here I am not going to be talking about. So the first one is what we call the expansion. So here we're not going to be talking about the decimal expansion because we're not using base 10 because of the fact that we divide by 3. So we will talk about, so the first one is the ternary expansion. Okay, so we know it's very easy to prove that in fact for every x in 0, 1, okay, your x can be written as besides 1. Okay, besides 1, let's say we remove 1. Okay, so it will be 0, a1, a2, etc. And basically this is equal to sigma of an over 3 to the power n from 1 to infinity. Okay, and if you want to catch 1, so 1, which is equal to 1 comma 0 0 0 0, it's also equal to 0 comma 2 2 2, etc. Okay, and why? Because sigma of 2 to the n, 2 over 3 to the n from 1 to infinity is equal to 1. Okay, so the problem with uniqueness of this expansion, I'm talking about in general, this expansion is the fact that sometimes the numbers can repeat themselves. Okay, uh, so but before we proceed a little bit more, let us understand something very interesting. So here it's not fully unique because whenever you have 1 and then 0 0 0, for example, you can remove, for example, if you have 0 comma something and then 1, and then after 1 comes 0 0 0 0, so what you can do, you can have 0 comma bum bum bum, and then that's 1, you put 0 and then you put 2 2 2 2 after it. So this is the only problem that you have, okay, where you have I mean, not you, I'm sorry, I should correct myself. It's just to say that you don't have uniqueness. You can always do this kind of stuff. But, if you look at, for example, let's start with just to see the relationship between this and the counter set. Let's take, for example, a number x, which is 0, comma, and we put 1, okay, and which is 1/3. But what I want is not to put 0 0 0. So put some numbers, okay, so a2, a3, etc. But I don't want the an's all to be equal to 0, not all. So at least one of them is not equal to 0. Okay, at least one. So in this case, what happened is your x is going to be strictly bigger than 0.1, and also less than, so we can have 0, 2. Okay, so in the ternary expansion, what is 0 comma 1? That's 1/3, and 0 comma 2, that's 2/3. So you see, the ones for which the first one is 1 are the elements that you removed in the first construction. So your x here does not belongs to E1. Okay, let us look at now if you have 1. So assume that you don't have 1 in the first one. So your x is equal to 0, a1, but you have 1 here, a3 in a2, etc. But I'm assuming that all the a3, etc., etc., are not equal to 0. So an not equal to 0, okay, for some n greater than 3, and here not all n greater than 2. So in this case, what's going to happen is that your x will be greater than 0 comma a11 and less than 0 comma a12. And what's interesting is that depending on A1 here, either you are in either you are in this one or this one. If A1 is equal to 1, you are here. And if A1 is equal to 2, you are here. In other words, you are not in A2. Okay? So this x here is not in A2. Okay? So by completing this construction, what happened is if you take x which belongs to C, if and only if your x is, of course, I'm removing 1 because 1 will have the 0, 2. So it's equal to uh, 0, comma, a1, a2, etc. Okay? And what happened is that the AIs are all 0 or 2. Okay? And including if you have that 0, because you may, and it's unique, in fact, huh? Except without 1 is unique. This ternary expansion is unique. Okay? The problem is, for example, 1/3, which is in C, or 1, which is in C. And in this case, what happened is that you have 0, see, these numbers here, okay? 0, A1, A2, AN, and then you put 1, and then you put zeros, okay? So these numbers here are dangerous because they have another expansion in the base, which is 0, A2, AN, and then the 1 becomes 0, 2, 2, 2, etc. So you see, the second one, this one is unique, and there is no ones. So you may have this problem. That's the only case where the elements can be in C and they have a 1. But after the 1, you have only what? Zeros. If you don't, that number is not in C. Okay? So what we are going to do is ignore this one. And in this case, all of them will have only 0 or 2 in a unique fashion. Okay? In a unique fashion. Okay? So we have to be careful when the sequence gives you only 2's after a certain n0. Okay? Great. So now, this shows that you have what? You have a kind of one-to-one relation between C and 0, 2 to the power n. Okay? And in this case, it's very easy to see that so there is a one-to-one mapping between C and 0 to the power n. So right there, we have a beautiful result, property, that C is uncountable. It's a classical, okay, result on coming from 0 to the power n, which shows, so of course this is of course from set theory, if one is uncountable, because we have a one-to-one mapping onto and mapping bijections between these two sets, they have the same cardinality, the same number of elements, so if one is uncountable, the other one is uncountable. So the proof, very easy. It's classical, huh? But let's do it. Assume that the set 0, 2 to the power n is countable. Okay? And let's write xn is a sequence, huh? Okay? It's a sequence of zeros and twos, okay? So these are, assume that this set, sorry, let me rewrite it, okay? Assume that 0, 2 to the power n is equal to xn for n equals 1, 2, etc. So, because you are assuming that it is countable, so if we have to assume that if the set is countable, then we have this. And your xn's are just sequence of zeros and twos, okay? So your xn, let's write it as a I of, sorry, let's we need a good notation. That's going to be a problem. A sub uh, n of I, okay, with a sub n of I equals 0 or 2 for I equals in n. So it's a sequence of zeros and twos, okay, but it depends on n. So now take x to be equal, okay, so for the first one, we look at a11, okay, so we are going to take, so we'll take 2 minus a1 of 1, comma. The next one is going to be 2 minus a2, 2, okay? And the nth one will be 2 minus a, n, n, etc. So what's special about x? X is different from xn for all n. Why? Because if you look at the nth element of xn, okay, so the nth element of xn, we get one has of xn is a n of n, while of x is 2 minus a n of n, which are different. These two numbers are different, and that's why this element x. But x belongs, obviously, to 0, 2 to the power n, and is not one of them. So this is your contradiction. So the Cantor set is uncountable. So next, what we are going to show is something very interesting, okay? At the same time, we're going to show that that the Cantor set is perfect, okay? As well as nowhere downs, okay? So, but let's start first by some basic property that will help us in the conclusion that we said, okay? Let's put as a remark, and then of course we can state the result afterward. So remark, let x belongs to C. So we know that x is equal in a unique fashion 0, comma, a1 in the ternary expansion, a2, etc., where the ai's are either 0 or 2. Okay? Great. So now what happens if I take xn equal 0, comma, a1, a2, an, and then I put zeros. Okay? And yn, which is 0, comma, a1, a2, an, and then I put 1, okay, 1, 0, 0, 0. Okay, so because they have the first block, which is the same, then it's very easy to see that x minus xn, okay, is less or equal than 1 over 3 to the power n. Okay, you can put 2 even to make it sure that. And the same with x minus yn is less than 2 to the 3 over n. Okay, because that's the maximum you can have on the remaining tail. Okay, so maybe not n for yn, maybe n minus 1, but it makes no difference whatsoever. Okay, so what happened? First of all, it's obvious that xn belongs to C, and this one does not belong to C. Okay, so your point x, in fact, you can approach it, but different. They are different from. I'm assuming that the AIs. So this is. I'm assuming that they don't. In other words, you do not have your x here. I'm assuming that I don't have zeros here. So if your in keep coming without zeros, they are all different from from x. Okay. So we'll see what happens if you have zeros afterward. But in any case, so these elements here, they can get closer and closer to x. Okay? So this tells you that if x is of this case without zeros as a tail, okay, then it's interesting that you can approach it by elements from C and the element not from C. Okay, which tells me that every element of this form is a limit point of C or an accumulation point of C. Okay, great. As for the case when you have 0, 0, 0, zeros, then let's look at it next. So you have x, which is 0, a1, and we assume that after a certain n0, you have 0, 0, 0, etc. So what you do for the x ends, you go a1, an, okay? I'm sorry, not an. So let's call this one k. So we don't k, and then you go 0, 0, 0, and then wherever you go 2, 0, 0, 0, 0, 0, okay? After n, okay? And it's gonna be as close as you want from x, while the other one, okay, will take 0, a1, ak, 0, 0, 0, and then we put 1, 1, 0, 0, 0. Okay, so again, you are going to have the same properties. The xn approaches x in C, and the yn's are not in C, and they still approach x as close as you want. Okay, so this tells me what? First of all, that property, next property, that any element of C is an accumulation point. Accumulation point of C. Okay, that's number one. And this is the definition of what's known as, so that's what we proved. Now you can approach x with any element different from x as close as you want. Okay, so this tells us any element of C is an accumulation point of C. Therefore, C is what's known as a perfect subset of R. Okay, so C is a perfect subset of R, and we know there is another property, another exercise that you can find on my web page, that perfect subsets, non-empty perfect subsets which are closed, are in fact uncountable. There is another proof which we can show that closed perfect subsets of R are in fact uncountable. Okay, and next, okay, it's easy to see that, okay, the next property, okay, if you take any open set, okay, let O be an open set such that C intersect this open set is not empty. Yeah, so let X belongs to C intersect O. Okay, then X which is in O, there exists an open interval, X minus R, X plus R, which is going to be in O. Okay, and what's interesting is that there is no way you can find an interval, okay, such that X minus R, X plus R cannot be in C. So in other words, there is no way you can find an R, no R. Okay, so here there exists an R such that you are in because it's open, but no R. Okay, for any R positive. Okay, we have that X minus R and X plus R is not in C. And the reason is because we said we can find what? Points, these yn's, which are as close as we want from X, that are not in C. So if n is large enough, okay, so if n is large enough, we are going to have then 2 over 3 to the power n less than r, and that yn, okay, which belongs to x minus 2 over 3 to the power n, x plus 2 over 3 to the power n. This one, the yn does not belongs to C, and this one here can be inside x minus r, x plus r for any r positive. Okay, so when you start with an r positive, you can find an n large enough such that this interval x minus 2 to 2 over 3 to the power n, x plus 2 over 3 to the power n is going to be inside. But that interval here contains the yn, which is not in C. Therefore, there is no way you can find an interval inside C. So in any open set that intersects C, there is no such interval that's going to be inside. You can find elements which are not, no interval will be inside C. And finally, let us put a quick remark before I close this basic lecture on Cantor Set. Let us look now at how much did we remove. Okay, so let us look at this remark would be useful when we deal with the measure of sets, because we said everything here is Borelian because you are dealing with closed sets and open intervals and closed intervals, and C being compact, it is Borelian anyway. So, but this remark will be very interesting. So again, let's go back and say, okay, so E1 that we have left, okay, we removed one interval, okay, so let's call that interval O1. That was, if you remember, 1/3, 2/3, okay, and then the O2 was the union of two intervals, two open intervals, okay, each had a length of 2/3. So this one has a length 1/3, and here two intervals, disjoint of course, with the length 1/9, each one of them. Okay. In O3, we have a union of four open intervals that we removed. They are disjoint, and each one of them has a length of 1/27. So when we go to ON, is a union of 2 to the power n minus 1 open intervals, disjoint, and each one of them has a length of 1/3 to the power n. So these intervals, if you take the union of all these open intervals, it gives you an open set, okay, and that's the complement of C. In other words, that C is equal to 0, 1 minus this open set, okay? But if you look at, they are all disjoint intervals that you're removing, okay? So if you take the sum of the length of all these intervals, you are going to find that this is equal to 2 to the power n minus 1, 3 to the power n, from 1 to infinity. And that's the length or the measure of O, okay? Which is, it's interesting, 1/2 sigma 2/3 to the power n, from 1 to infinity, and this is equal to 1. In other words, what we removed is almost like the entire interval 0, 1. What's left has what's known as measure 0. So basically, what's left here, the measure of C, is equal what? To 0. It's almost very interesting. A set that is uncountable, perfect, and it has a measure 0. Thank you.